Okay, so let us look at another possible scenario here. The conjugate acid of a weak base is itself a weak acid. So we're going to be not considering the anions behaving as bases, but we're going to consider the bases, a base, its conjugate, its cation being an acid. All right, so let's look and talk through these few questions here. NH3. What is NH3? Pick one. Well, it is a weak base. How do I know that? Well, when I see a nitrogen with 3 bonds to it, that is a giveaway of a weak base. So it has 3 hydrogens, it's a base. If it was 3 CH3 groups, it'd be a base. 2 hydrogens and 1 CH3 group, a base. If it has 3 bonds to that nitrogen, it is going to be a proton acceptor. It's going to be a base. It's not a strong base because strong bases are metal hydroxides, okay? And just because it has H's doesn't mean it's an acid. Generally, our H's are written at the beginning if they're acid or donatable protons. Okay, so NH3 is a weak base. So what does that make NH, or what is its conjugate acid? That's what I should ask. If NH3 is a weak base, which one of those is its conjugate acid? Well, a conjugate acid is what it becomes after it does the acid thing. It accepts a proton, the base thing. It's a proton acceptor. It accepts the H+. What does it become? NH4+. So we have that NH3. We put an H+ on it. It becomes NH4+. That is its conjugate acid. All right, now you're going to work this one. Kb I'm giving to you. Kb of ammonia is 1.76 times 10 to the minus 5. What is going to be the Ka of its conjugate acid? All right, hopefully you picked B. And let's set it up here on the screen, the computer screen for a moment. We've got the Kw equals Ka, which we're trying to solve, times Kb. So Kw divided by Kb is Ka. 1 times 10 to the minus 14 divided by 1.76 times 10 to the minus 5, and that is going to give me the 5.68 times 10 to the minus 10. Now if you set it up, once again, if you set it up like this, but you did not get this answer, it's how you're using your calculator, and you need to make sure you get help with that. Learn how to use the exponent key on your computer. So we've got ourselves ammonium chloride, NH4Cl. Let me get my pen behaving a little bit better. It is going as an ionic compound 100% break apart into its ions. We have the NH4 plus ion and we have the Cl minus ion. Now we have worked through in the previous work that this is an acid. And so we'll just go on as if we'd already talked through this. We know that this is a one-way reaction, so if we put 0.22 molar in, it 100% breaks apart into these ions. For every one of these, you make one of these. So this goes away, and we have 0.22 of this and 0.22 of this. Now what does the rookie do? The rookie says, I'm cutting it in half, so let's make half of it this and half of it that. That's not what we do. This makes one of these and makes one of those. So whatever you had here, you get the same number for both of those. All right, this is neutral. It is not going to do anything because it is a conjugate base of a strong acid. Conjugate bases of strong acids are neutral. It's this guy that we need to write the reaction for next. So NH4+, it gets placed into water. And it does. And I will always do that. I will always include my water. Whether it's an acid or it's a base, I will write plus water. And then I say, okay, it's going to do the acid-base thing. This is an acid. Acids are proton donors. Who does he donate to? The water. So it is weak, so I have the double arrows. I donate to the water. That's going to leave me with NH3. And the water becomes H3O plus. All right, there we go. So there's my reaction. Equilibrium. We will need an ICE table. hold off on the ICE table for just a moment. Let's write the K expression. Is it Ka or Kb? This is an acid, right? So we need Ka. Go ahead and write the expression, the law of mass averages, mass action, that's what it's called. I just call it the equilibrium expression, okay? So I write it. Remember, we leave out the water because we leave out liquids. So I'll hold that ready because I'm going to need to use it. Now let's fill in our table. Don't care about that. This is what I care about. It's NH4. I'm starting with, for this reaction has a chance to take place, 0.22 molar. Don't care about the water. None of this, and essentially none of that. I consume, it's going to produce, right? So I consume some of this, produce X over in this side. Now I'm going to have 0.22 minus X. I'm going to have X, and I'm going to have X. So I write my expression, I fill in my table, now I'm ready to put information into my expression. Ka. In the problem was given Kb. What did we determine in the previous slide was the value of Ka? It was 5.68 times 10 to the minus 10. Okay? And that's going to be X times X divided by 0.22 minus X. Very small K. Assume that X is very, very small. And when you do that, you can ignore the X. Okay, so we take it out of the picture. So now we keep solving for X. 5.68 times 10 to the minus 10 times, we're trying to get the 0.22 up here. 0.22 is equal to X squared, but I want X. Now in reality, there's a positive solution and a negative solution. We don't want the negative solution because we don't want a negative concentration. The positive solution for this problem is 1.11 times 10 to the minus 5. We check our assumption. Is X much, much smaller than 0.22? Certainly. If I took this and subtracted it from 0.22, I'd still get 0.22. Great assumption. Check. Now, we have to go back and say, I've solved for X. What did they want to know? Wanted to know the pH. What does X give me? X gives me the concentration of H3O+. So if I take the negative log of 1.11 times 10 to the minus 5, I will have the pH. And the value for that is 4.95. Now don't get an answer without thinking, is that logical? We established that this is an acid. We're producing H3O+. We should have a pH less than 7. pHs less than 7 are acidic solutions. So you take your salt, you break it apart 100% to consider the concentration of the ions. Which one of these ions are acidic or basic? Take that one and write its reaction and do what we've been doing for quite some time, the acid, in this case, equilibrium. Okay, let's see what's next. All right, when given a problem at random, okay, I'm talking about salt, so it's easy to figure out, but when you're given a problem at random and somebody just throws it to you on a test or whatever, you really have to figure out what you're dealing with first. Is it an acid? Strong or weak? Is it a base? Strong or weak? Is it a salt? I don't know. Is it an acidic salt, a basic salt, or a neutral salt? There's a lot of thinking through before you can ever start writing reactions. So here is a problem. We're determining the pH of HCOO in A. I want you to first answer this. What is HCOO in A? Is it an acid? Is it a base? Or is it a salt? And if it's a salt, tell me which one of those fit with it. Well, this is a salt containing a conjugate base of a weak acid. So let's see how we know that. I'll write on the screen here. This is written in a strange order, and it's because organics very often write it this way. But when I see that metal, metals are always cations. So there's my cation. So this must be the anion. All right? So when this dissolves, it's going to break apart into Na plus and HCOO minus. So it is a salt. Some of you might have said an acid. Oops, sorry. Some of you might have said an acid because it has an H at the beginning. And very often an H at the beginning is the giveaway of that. I don't want to leave this problem without saying that it would not be uncommon to see this written this way. NaCO2H. No, it's not written that way. Sorry. It's NaCHO2. That is how you would very often see this written if it wasn't an organic person. Organic person would always write it the way you see it here. An inorganic person would more often see it written this way. But either way, we see this sodium. We know that that has to be the cation, and it's going to break apart into ions. So this ion could have been written as CHO2-. That would be another way to express that. All right, then we know that this guy can't donate an H plus because it doesn't have one. Cations don't accept H pluses, so it's a neutral cation. And this guy is an anion, so it could accept a proton if, in doing so, it wasn't a strong acid. Well, HCOOH is not on my strong acid list. Therefore, this is a weak acid, and therefore this is its conjugate base. It is weak. Okay, so now we're ready to work this problem. We've established that HCOONA is a salt that breaks apart into Na plus HCOO minus. We established that this was the neutral ion, but this was a proton acceptor, therefore a base. We know that we're placing 0.10 molar into this solution, but it 100% breaks apart into these ions. So this goes away, and we're left with those concentrations. Now we pick up with that base. As a base, when it sits in that water, it will be a proton acceptor, accepting a proton. So write the products. You write them and then restart it. The products would be HCOOH and OH minus, because the water gave its proton, leaving you OH minus behind. It's an equilibrium because that's weak. So we'll do an ICE table. I'll go ahead and put the 0.10 there and stop for just a minute and write the expression for this equilibrium. The K, is it an A or B expression? Well, that's a base, so it's a KB expression. It is the HCOOH concentration times the OH minus concentration divided by the HCOO minus concentration. Hold that so I can plug things into it and solve for X. Finishing the I line, I have nothing here and essentially nothing there. I consume of this side, I produce on this side, and I have 0.10 minus X. I have X and I have X. Remember, the X's are because there's one coefficient with these, and there are not always one coefficients, but with acids and bases they always are, because you're always transferring one proton in the acid-base reactions. So now let's plug things in. I need a KB. They gave me Ka of the acid. So Kb would be 1 times 10 to the minus 14 divided by the Ka that we see on the screen, 1.7 times 10 to the minus 4. The value of that K is 5.9 times 10 to the minus 11. And that is equal to X times X divided by 0.10 minus X. So that's X squared divided by 0.10 minus X. We look at our very small value of the equilibrium constant and assume that X would be very, very small, and I can ignore it. And then I will solve for X. I will have 5.9 times 10 to the minus 11 times 0.10. That's equal to X squared. So if I take the square root of both sides, I get two solutions. I'm only interested in the positive solution. X is 2.4 times 10 to the minus 6. I ask myself, was that a good assumption? Is it much, much smaller than 0.10? Certainly it is. So yes, that's a good assumption. I solve for X, I go back to the problem, it's asking for the pH. It doesn't always ask for the pH. Could ask for things like percent ionization. It could ask for what's the concentration of acid. It could ask various things, but it's almost always asking what's the pH. So, how do we get the pH? Well, we come back up here and see that X is the OH minus concentration. So if I take the negative log of this number, what will I have determined? Okay, what is that? -6. I will have determined the pOH. So what is the pOH value in this case? It's 5.62. Don't just blindly take the negative log and think you've got the answer. This is pOH. We want pH. We know that pH is 14 minus 5.62, and that's going to be 8.38. Now, should it be above 7? Well, we established that it was a base. Bases should be above 7. So there is another example of a salt solution. Now, salts, calculating pH of salts, are the most challenging for students because you've got two reactions you've got to write after you recognize that it's a salt. So I'm going to work through one more example with you. Okay, we have one more to work, and I'm doing lots of examples of this because it's really challenging for students. But realize that if you're getting tired, you can stop the video and come back to it a little bit later. Because when I want you to work this one, I want you to stop and see if you can do the next step and then resume and see if you did it right, okay? So I have this substance, which is CH3NH3Cl. And I want to know the pH of this solution, and the concentration, of course, is given to me. This is not a base. It has nitrogen, and it has 1, 2, 3, plus this group, 4 things attached. That's always going to make a cation, and there's its anion, okay? So recognizing this as a salt and breaking apart into this plus this is very important. Ionic compounds always break apart 100%. There's the cation, there's the anion. That's one of the challenges for students. Now we have to look at these two guys and decide, are they acidic, basic, or neutral? I'll start with this one. If it accepts a proton, which is negatively charged, we can conceive of it doing so, it would become HCl. That's on my strong acid list, so it will not accept that proton. It's neutral. Okay? We look at this guy. We have a nitrogen. We've got these 4 groups. It's positively charged. It's not going to accept a proton because it's positively charged. Like charges repel. It is going to donate a proton if it has one. Does it have an H plus on it? Yes. It's got 3 H's here. One of those could be donated. So this is a proton donor, which is an acid. Certainly not a strong acid, is it? It's not my strong acid list. So the next thing that we have to do is take that acid, CH3, NH3+, and have it do its acid thing in water. So write the reaction of it behaving as an acid. Remember, stop the video and try and resume and see how you did. All right, equilibrium arrow because it's weak. If it donates, it doesn't donate one of these. It always donates one that's attached to the nitrogen. So we're down to 2 hydrogens, no longer a charge. It donated an H plus to the water. The water became H3O+. Now it's in equilibrium and it needs an ICE table. What did we say this was? An acid or a base? It's an acid. So we'd write a Ka expression. Products, CH3NH2 times H3O+. Okay? CH3NH3+. Hold that, come up here, fill in our table. What's the concentration of this? Well, let's go back up to the concentration of the whole thing. It was 0.05. That goes away in one-way arrow, gives me this much of the 2 ions. So this is 0.05. Do I have any other zeros? Nope, I don't. So that is the concentration of that. Lots of water, don't care about it because it's not in my equilibrium, and some zeros. Now it's going to produce some of these, so it's going to use this up. The 1 to 1 to 1 coefficients means I produce like this and have 0.05 minus x, x, and x. Now let's plug in values. Look at the information. I was given a KB. I need a KA. So I take 1 times 10 to the minus 14 divided by 4.4 times 10 to the minus 4. That's going to give me the Ka that I need. It's 2.3. Yep, 2.3 times 10 to the minus 11. And now I'm ready to plug in my E line into this expression. X times x. You see a pattern happening here? It happens over and over again. But when you go back and start doing some from the previous chapter, remember there's coefficients other than 1. It doesn't always look like this. How about the assumption? Can we assume that x is much, much smaller than 0.05? Sure we can. That's a very tiny KB value or Ka value. So I can ignore this x, okay, and I can solve for x. So we'll have 2.3 times 10 to the minus 11 times 0.05, so I'm getting this up here, is equal to x squared. Take the square root of both sides, okay, and then that will give me an x value equal to 1.1 times 10 to the minus 6. Check your assumption. Is that very small compared to 0.05? Sure is. It's a good assumption. Now go back and look at the question. What was asked? What is the pH of the salt solution? Well, X is the H3O plus concentration. So if I take the negative log of 1.1 times 10 to the minus 6, what will that have determined? It will have determined the pH because that is the H3O plus concentration. This gives me a value of 6 for the pH. Okay. Is it exactly? Oh, I know why. I don't know this to 2 decimal places because I only know this to 1. Okay. So I only know this to 1. If I only know this to 1, then I only know this to 1, and that's what I know as the pH of this solution. We checked if that makes sense. This was an acid. We should have a pH less than 7. We do have a pH less than 7. So lots of examples of calculating the pH of the salt. But where does the challenge lie? Oh, let's go back to that. Not quite ready for that yet. I need to tell you about one other place. We haven't thought about this yet. One other way that a cation can be acidic. Here's a cation that's acidic because it has an H plus it can donate. We kept seeing things like Na plus and saying that's neutral. It doesn't have a proton to donate. If it is a cation without an H on it, you wouldn't think it could donate a proton and be acidic. But there is a special scenario here. If you have a small, highly charged metal cation, it can make a solution acidic even though it doesn't have any H's to donate. So the question is, how in the world is that possible? You need to know that it is possible, so that's a statement. Small, highly charged metal cations are acidic. Now what do I mean by small? Well, let's look at this periodic table. When I'm talking small, those would be things near the top of the periodic table. So there's a metal, okay? Boron's not a metal, but aluminum is. That would be small. Guys along here, they're small, okay? These are all small metals. I guess we could say these guys are small too. Now, highly charged. What do I mean by highly charged? 3 plus or greater. I would never consider plus 1 and plus 2 a high charge. Plus 3 or greater would be a high charge. So if we had something like iron with a 3 plus charge, that would be a small, highly charged metal cation, and it would be acidic. So we look at that and say, how in the world can that be a proton donor? Okay? It doesn't have an H plus on it. It is because of a side reaction that will take place, and let's look at this side reaction. All right, so I'm leading us down the road. If we had this ionic compound, iron 3 nitrate and dissolved it into water, it would have these iron 3+ ions, and it would have 3 nitrate ions, right? That's a neutral ion, and we have this Fe3+. Here's what happens. As soon as that iron with a 3+ charge dissolves into water, and it's floating around in there, it gets surrounded by the water molecules, all right? The oxygen is partially negative and will point in towards that positive charge. The oxygen, which is partially negative. So it'll arrange itself around that. Now, it is this guy, then it has all sorts of H's on it, doesn't it? How many H's do you see there? Well, 2, 4, 6, 8, 10, there's 12 H's on there. That's the guy that can donate. One of these H's can be donated to a water molecule, and there we see it now without its H. What does it look like formula-wise? Well, it has 5 waters attached plus an OH minus attached, and the charge went from a 3+ overall to a 2+ overall, and the water accepted that proton, which we see written right here, and has a plus charge. Okay? So that is how a small, highly charged metal cation can be acidic. It's not the Fe3+ by itself that's acidic. It is this whole conglomeration that forms in the water that it then becomes acidic. So you could take an iron nitrate solution, like was written on the previous slide, and put a piece of pH paper in there or a pH probe, and you would see that indeed the solution is acidic. So here is an overall summary of classifying salt solutions, and in our next lesson I will walk through all of the possibilities of identifying whether a salt is acidic or basic. So it's an overview of everything we've discussed to this point.